Up to this point, we have built a structural ladder. Coherence above threshold produces stabilization. Directional variation produces metric structure. Non-uniform coherence produces curvature. Coherence redistribution produces dynamic geometry. Structural constraints narrow the form of geometric evolution. In the previous episode, we observed something important. The structure of gravitational dynamics fits inside this framework. But one question remains unresolved. What determines the strength of the coupling? In general relativity, curvature responds to energy density with a specific proportionality. That proportionality defines gravitational strength. In our framework, curvature responds to coherence density. But we have not yet determined the scale of that response. Structure alone gives form. It does not automatically give magnitude, so where does magnitude enter? To answer that, we return to threshold. Threshold is the minimal coherence required for stabilization. Below threshold, geometry does not exist. Above threshold, geometry appears. But threshold is not just binary, it defines a scale. The magnitude of coherence required to sustain closure defines a structural unit. Call this the stabilization scale. This scale determines how much coherence is required to produce measurable curvature. If threshold is extremely small relative to total coherence distribution, curvature effects will be weak. If threshold is large, curvature will be strong. So coupling strength is not arbitrary, it is tied to stabilization scale. Now consider dimension. Earlier, dimension emerged from minimal generating basis. The number of independent coherence directions determines geometric degrees of freedom. But dimension also affects scaling behavior. In higher dimensions, coherence may distribute differently. Gradient magnitudes scale differently, so coupling strength must depend on both threshold magnitude and dimensional structure. Now consider density. If coherence density is defined relative to stabilization scale, then curvature response depends on how coherence compares to that scale. Regions where coherence barely exceeds threshold produce weak curvature. Regions where coherence greatly exceeds threshold produce stronger curvature. But coherence cannot accumulate arbitrarily. Redistribution constraints limit concentration. This explains something subtle. Gravity is extraordinarily weak compared to other interactions. Why? Because stabilization threshold must be low relative to the total coherence content of most regions. If threshold were high, geometry would be unstable. The universe would constantly fluctuate between pre-geometric and geometric regimes. Stable, large-scale structure requires threshold to be small compared to typical coherence distribution. That small ratio translates into weak curvature response. Gravity is weak because threshold must be permissive enough to allow stable geometry across vast regions. Now consider coupling universality. In relativity, gravitational coupling is universal. All energy contributes. In our framework, all coherence contributes to curvature. There is no privileged subtype. Coherence density, regardless of source, influences geometry. Universality follows automatically. Now consider scale separation. At very small scales, coherence fluctuations may dominate. At macroscopic scales, averaged coherence governs curvature. This suggests that gravitational strength could emerge from coarse graining behavior. Microscopic coherence interactions may be strong locally, but average out across scale. What remains at large scale is weak net curvature response. This offers a structural reason for gravity's weakness relative to quantum interactions. Now, consider invariance. Coupling strength must remain constant across large-scale geometry. If stabilization scale varied arbitrarily across space, gravitational strength would fluctuate, but refinement constraints enforce global structural consistency. Threshold must be uniform across stabilized closure. Otherwise, geometric encoding would fragment, so coupling strength emerges as a global structural constant, not imposed, required for coherence of geometry itself. Now consider vacuum. In relativity, empty space can still possess curvature under certain conditions. In our framework, uniform coherence above threshold, but without gradients, produces flat geometry. If background coherence slightly exceeds threshold everywhere, small fluctuations may produce residual curvature. This resembles vacuum energy effects, but we remain cautious. The key point is this. Coupling magnitude is determined by the ratio between coherence density and stabilization threshold. Threshold sets the unit scale. Dimensional structure shapes how gradients translate into curvature. Propagation constraints determine how redistribution spreads. Together, these define gravitational strength. Now consider extreme cases. If coherence density approaches threshold from above, geometry becomes fragile. Curvature becomes sensitive. Small fluctuations may produce large geometric effects. If coherence density is far above threshold, geometry becomes robust. Curvature responds more gently to perturbations. This suggests that gravitational behavior may vary under extreme conditions. Such regimes could correspond to early universe states or high-density environments. But again, structural possibility is not yet empirical claim. Now step back. Why is this episode necessary? Because structural alignment with gravitation is insufficient without scale. Form without magnitude is incomplete. We now have both. Structural form emerges from coherence dynamics, magnitude emerges from stabilization threshold, and dimensional scaling. Nothing has been inserted externally. Now consider something profound. If gravitational strength is tied to stabilization scale, then measuring gravitational coupling is indirectly measuring threshold. Gravity becomes a window into pre-geometric stabilization. This reframes gravitational constant not as arbitrary, but as structural parameter. Now consider unification. Other interactions may correspond to different modes of coherence redistribution at sub-threshold or near-threshold regimes. Gravity corresponds to large-scale coherence imbalance. Other interactions may correspond to finer-grained stabilization modes. But that exploration belongs later. For now, we conclude, coupling strength is not arbitrary. It is determined by stabilization, threshold, magnitude, dimensional structure of coherence, variation, scale of coarse graining, conservation and propagation constraints. Gravity's weakness is not mysterious, it is structurally necessary for stable geometry. And gravitational universality is inevitable once coherence density governs curvature. We have now built a bridge from pre-geometry to dynamic gravitation with scale. The next step is delicate. If gravitational strength encodes stabilization threshold, can we derive observable deviations in regimes where coherence approaches threshold? If so, the framework becomes predictive. And prediction is where philosophy ends and physics begins.